Hi, everyone. Today's lesson is going to be on forces of attraction, which is sort of what holds together molecules in a sample. The first thing we have to talk about, though, is the difference between these two root words, intra and inter. So, what is the difference? Intra is a root word that means within. So when we're talking about intramolecular forces, that's what's holding together a molecule. So if you look here between this hydrogen and this hydrogen is sharing an electron with chlorine and the chlorine sharing with hydrogen. That electron bounces back and forth and back and forth. And that bond that is formed is an intramolecular force. These are very strong. They're very hard to break. They take a lot of energy to break them. So, sorry, I'm trying to get something underneath my computer. So they are quite strong. They're quite hard to break. The difference between an intermolecular force, this is what's happening and what's holding neighboring molecules together. So you can kind of see in this image here, we see that we have intermolecular forces. So when you have something that's an ionic compound, or I'm sorry, a covalent compound, something like hydrogen and chlorine together. Chlorine has that slightly negative end to it. So you see that little negative charge. And the other side of a molecule, just like it, has a slightly positive charge. That positive and negative want to be close to each other. So the negative chlorine from this molecule and the positive hydrogen from this molecule will sort of attach themselves close to each other. These forces are not permanent. They do not last forever. They are not electrons being shared between them. They are simply just attractive forces that are holding them close by each other. So again, these are not permanent. These are not chemical bonds that are formed. A chemical bond is where electrons are being transferred or shared. This is just a force that's holding them together close by one another. So if we're looking at something like an ice cube melting, think to yourself, am I getting a new chemical compound after this change has occurred? So if I'm looking at melting ice, before it's melted, when it's solid ice, it's still water. After it melts, it's liquid water, still water. This is breaking intermolecular forces. I'm not breaking any chemical bonds in water. All I'm doing is just causing it to not stick together as well. And then if we look at the contrast, if I'm trying to burn wood, which is a combustion reaction, I know that there's a lot of energy that's released as a byproduct. There's a lot of heat. All kinds of stuff gets released when you burn something. And that's because we're breaking intramolecular forces. So as a result of this lesson, we're going to differentiate between those two terms. What are the intermolecular forces that we see in chemistry? What kind of force would be found within a substance? And then how do we know whether or not something is going to be what we call mixable or miscible? Sorry. So to review, we kind of reviewed this with the homework after the exam, but when we are looking at polar molecules, both of these things must occur. So you'll notice that I have and listed for in between these. It needs to have unequal charges from electronegativity, so big difference in electronegativity. But I also need to have an asymmetrical molecule. So what does that mean? If I look at something like CO2, okay, this is what the molecule looks like. And carbon and oxygen form a polar bond. So the electrons are moving towards the oxygen on both sides, meaning this side would be electronegative and this side would be electronegative. But if you look here, there's no area of the molecule where one side's positive and one side's negative. This is very symmetrical. So this cannot be polar. This is nonpolar, okay? It's impossible for it to be polar because we have that symmetry. If I'm looking instead at something like HCl, what I see here is the electrons are moving towards that chlorine, and that side becomes negative, that side becomes positive, okay? I don't know why this is happening. Okay, so that's that down there. Okay, so sorry. Okay, I think we're in the right place. Sorry, I was having some computer issues, some glitching. So if I want to have something that's polar, it needs to be not only a strong difference in electronegativity, but also asymmetrical. So I'll show you an example of what that looks like. Nonpolar molecules then are where you have equal charge distribution. So you'll see that I use this term equal here, equal charge distribution. That means the electrons are shared equally between them. Or I have symmetry. So if I look at the example of that CO2, where it was symmetrical, okay, where those electrons were moving equally this way and equally this way, that symmetry makes it nonpolar as well. So nonpolar things can be either a small difference in electronegativity or they can be symmetrical. It can be either one of those. So what are some examples? We look here at our polar examples. We have hydrochloric acid, so H and Cl. Electrons are moving towards the chlorine. Here we have ammonia, that N is more electronegative than the hydrogens. So they move towards the nitrogen, the electrons, they want to move towards the nitrogen. And that end of that pyramid becomes a little bit negative. Same thing we see here. That central carbon is bonded to 3 hydrogens, and then there's a chlorine up top. That chlorine disbalances the charges. It's not symmetrical. But in comparison, down here at these 2 nonpolar ones, you can see that we have a significant amount of symmetry here. So we have very symmetrical. All the electrons are being pulled equally in equal directions. I don't have an opportunity to have positive or a negative end here because they're all even. So when we look at intermolecular forces, these are going to be the forces between those neighboring particles. So they're not chemical bonds. These are just holding particles close to each other. The weakest is... So of these forces, we rank them from weakest to strongest. The weakest that we see are what are called London dispersion forces. So these are super weak, not strong at all, very easy to break. Dipole-dipole forces are then next. We also see hydrogen bonding and ion dipole. So the strongest of these 4 is this ion dipole attraction. The weakest are dispersion forces. Altogether, we call these van der Waals forces. So these intermolecular forces between different particles, these are called van der Waals forces. So before we talk about them in detail, let's just take a minute to look at what we call hydrocarbons. So hydrocarbons are just carbons and hydrogens put together. You have methane, butane, ethane, heptane, all these different hydrocarbons. And as you start adding more carbons to it, you'll notice that this boiling point data varies a little bit. But I also didn't put this in order. So if we rearrange it, put it in order, do you notice any trends now? As we increase the number of carbons and hydrogens we have in this molecule, so we compare like methane to, let's say, octane, the boiling point increases. So the more atoms that are in this molecule, the higher the boiling point. And boiling point is a measurement of how much energy it takes for me to change something from a liquid to a gas. Changing something from a liquid to a gas means that I'm breaking intermolecular forces because that's what's holding the liquid together. So if I need a lot of energy to boil something, to turn it into a gas, that means it's held together stronger than something that has a low boiling point. So if I look in comparison, methane to octane, they're both carbons and hydrogens. We'll see that they both have the same kind of intermolecular force, but one of which is much stronger. And it's because this compound has much, much, much more carbons and hydrogens in comparison. So dispersion forces, what are they? They are temporary. They are temporary attractive forces in nonpolar particles. They also create temporary dipoles. So I'm going to show you what that looks like here in this video. You're going to see it pop up here in a second. But what's happening is that temporary dipole forms. So when the electron is over here on this side of the molecule, it becomes negative. And then if it goes to the other side of the molecule, that end becomes negative. So the electrons are bopping back and forth throughout this molecule, meaning that that dipole switches. So it's on one side, then the other side, then one side, then the other side, then one side, then the other side. And it does this for eternity. It never stops moving. It's always bouncing back and forth. So the side of the molecule that's going to be positive or negative just changes based on, where the electron is at that moment in time. So in this example, here's the electron, it's negative. If the electron moves to the other side of the molecule, that side now becomes positive. So as those electrons move back and forth, we form dipoles. So they're stronger in larger particles, which is what we saw in the last slide. So with that hydrocarbon data, the bigger my particle, the more London dispersion forces I have. And also the stronger they are if we put them close together. So if we put those molecules close together, they're going to have a stronger London dispersion force. The farther apart they get, the weaker that force. This force is in every particle that exists in the universe. Even if you have something like an ionic compound, there's still some dispersion forces. It's just that they are not the strongest force. These are pretty weak. They're pretty easy to break. It doesn't take a whole lot of energy for me to break them. But we do find them in pretty much every molecule that exists. Not pretty much every molecule that exists. So we can sometimes call these London forces. So I usually call them London dispersion forces. So here's an image just kind of showing you what this looks like. Here we have two nonpolar atoms or molecules. Doesn't really matter what they are, but they're nonpolar. And when the electron moves to one end of the molecule, that side becomes a little bit negative and a little bit positive. The negative end is where the electron is. So that momentary dipole, that just split second where the electron is on the one side, changes to negative positive, and those atoms and molecules will align themselves. So the positive is near the negative. So what kind of particles attract each other? Polar molecules attract other polar molecules, or ions, things that are charged. Nonpolar molecules, however, are not attracted to polar molecules. They have no interest in being around polar stuff, couldn't care less. They don't in any way attract them. So the next kind of attraction that we see, it's a little bit stronger, is what we call dipole-dipole attraction. In this, it's happening in polar molecules. So the difference, the last one we saw, it was in nonpolar molecules. Now, dipole-dipole has to happen with polar molecules. Okay, so polar molecules, they're forming that permanent dipole because one of the elements in that molecule is stronger than the other one in terms of electronegativity. One of them gets to have the electron more than the other, and that side becomes negative wherever the electron goes. So I'm going to show you what that looks like here in this quick little video. So you have this element, the blue one, which is going to hog the electron more than the red one. That causes that dipole to occur, that partial positive, partial negative. And then the attraction between neighboring particles forms. That's what we see, those little dotted lines in between them. Those are the intermolecular forces. That little dotted line is the dipole-dipole interaction. That doesn't necessarily mean it's always going to be there. They can form and disform often, but we will see them coming and going. But those dipoles are permanent. So the strength of that force is going to depend on the difference in electronegativity. The bigger the difference, the more polar, the more stronger your intermolecular forces. And we also see that those oppositely charged ends are attracted towards one another. So here's an example of a pretty common dipole-dipole interaction where you have hydrochloric acid. So this is a covalent bond holding it together, very hard to break. And then that intermolecular force is much weaker in comparison. It's still a dipole-dipole interaction. It's still strong compared to a London dispersion force, but it's not that strong. Then we see something strange. So these are all covalent compounds. They're all two nonmetals. But you'll notice that these elements, which are from the same column in the periodic table, oxygen, sulfur, selenium, tellurium, the boiling points for oxygen is kind of an anomaly for water here. So notice that its boiling point is 100, whereas the next one down in the column with sulfur, the hydrogen sulfide, that's going to have a really drastic difference in boiling point. So why? Why does that happen? The reason being is because there are certain elements that form polar molecules where the difference in electronegativity is outrageously strong, like the strongest. When we see hydrogen bonded with nitrogen or oxygen or fluorine, these three elements and these three elements only, we will form what is called a hydrogen bond. This is a special type of dipole attraction where the difference between the electronegativities and the hydrogen and oxygen is very drastic, meaning that they're kind of ultra polar. So your oxygen end of the molecule is going to be ultra electronegative, and this side is going to be ultra electropositive. What then occurs is you have a stronger intermolecular force. So typically these are going to be stronger than your normal dipole-dipole forces. So if we're looking at something like water, we know that water is held together pretty strongly because it takes a lot of energy to boil it. It has a really high surface tension. It's very strong in terms of its molecular structure, like when it freezes. So it's how we see water having really specific behaviors. We wouldn't expect water to do the things that it does because it's polar. But because it's bonded with hydrogen bonding and its intermolecular force, it's very strong, very hard to break. So these little dotted lines here that you see forming and breaking and forming and breaking, these are the intermolecular forces, those hydrogen bonds. These are very strong dipole-dipole interactions. So it's because they just are outrageously strong in between the hydrogen and the oxygen. They're very polar. So this is also why we see that ice is less dense than water. Typically, if you have a solid, it is going to be more dense than its liquid form. This happens for pretty much every chemical that exists in the universe except water. When water forms ice, those hydrogen bonds form and are being held in place. And when that's being formed, that empty space occurs. And that empty space makes the object less dense, which is why ice floats when we would typically expect the solid to sink. Hydrogen bonds are also what hold DNA together. So if you're looking at a molecule of DNA, you have two sides of your lattice that will then bond together and twist, and that's how you form a double helix. It's held together with hydrogen bonds. So these are really strong bonds. They're hard to break. That's what you want to have happen. You don't want your DNA just falling apart. You want it to stay nice and held together. So hydrogen bonds are quite important biologically. Then we have our strongest interaction. This is what's called an ion-dipole interaction. This is where you have something that's ionic dissolved in something that's polar. So your polar molecule has that permanent dipole. Your ion is charged because the electrons have been transferred. So when you form an ionic compound like salt, sodium chloride, that transfer of electrons causes a permanent plus and minus charge. The ion is then attracted to the polar molecules that have dipoles. So if you look here, the chlorine, which is slightly negative, or I'm sorry, the chlorine is negative, it is attracted to those slightly positive hydrogens. So you can see the water molecules sort of oriented themselves to surround that chlorine. So the hydrogens are closest to it. In the case of the sodium, which is positively charged, the water molecules here have aligned themselves to be the negative end of it, the oxygen end, facing the sodium. So the strength is going to depend on how close together they are, how big of a charge it is, and also how big is that dipole. So is the polar molecule really, really, really strong dipole or not so strong dipole? This is why we'll see water has a really good ability to dissolve things like salt. It's because it's very polar, and polar things dissolve ionic things very well. The more polar it is, the better it's going to dissolve an ionic compound. So that leads us to our last little thing to talk about, which is miscibility. So when do things mix together? You've all probably seen at some point or another oil and water. You know, oil and water does not mix. Doesn't matter what you do, it's always going to separate. This has to do with polar and nonpolar molecules. Polar molecules will mix with polar molecules and some ionic compounds as well, but they will not mix with nonpolar. They are immiscible. So what I'm going to show you in this quick little video here, there's 3 different setups. 3 of the beakers are green and have just food dye water, so nothing too special. In this first beaker, we have ethanol, which is a polar solvent. Here we have hexane, which is a nonpolar solvent. And here we have butanol, which is kind of somewhere in between. So it's polarish, but not super polar. So you'll see when these two are mixed together, polar and polar, they're miscible. They mix together very nicely. You don't see any distinction between the water and the ethanol. They mix. Okay? Looks just like one sample. You'll notice though, when this water is poured into the hexane, what immediately happens? They separate. And no matter what you do, you're not going to get them to mix together because hexane is nonpolar and water is polar. And then here, where you have the water and the butanol being a little bit more polar than we would see the hexane, you'll notice that as it's mixed together, it looks kind of like our first beaker. But as time goes on, it separates a little bit more. But does it separate as much as the hexane? Not quite. You kind of have this interlayer where they're mixing a little bit, but just not that much. So when we're talking about miscibility, it has to do with how well those materials are able to dissolve in one another. Polar dissolves polar, nonpolar dissolves nonpolar. They do not mix. So there's like a phrase we use in chemistry, like dissolves like. So that's something to keep in mind with, like, in terms of how this works. Why do some things dissolve in others? It's all to do with the intermolecular forces.